in this video, we're going to explain some of the intuition behind the previous results. In particular, why does the backward current on a transmission line have the negative sign? So let's begin with the model. Here's the voltage source V. And of course, there is a voltage wave that's launched across the transmission line. And this transmission line is grounded. So the voltage is with respect to ground. The wave goes from the source to the load, which in this case is an open circuit, and the amplitude is V plus. So there's a voltage wave, as we saw, that goes down the line. The line has some characteristic impedance, Z0, and the load here is a simple load. It's an open circuit. Now, associated with the voltage wave, there's a current wave, and its amplitude is I plus. So the current goes down the line. Now, it's open circuit. So Sam, what's the current in an open circuit?
Well, it's supposed to be zero. Nothing can go through an open circuit.
Nothing can go through an open circuit, but in general, we'll have some load here, and current always has to have a return. So the return current is this way. This is a return. So in terms of the sense of the current moving in this circuit, it's clockwise. It goes down to the right and comes back to the left. And so there's the sense of the current, clockwise sense. So let's send the wave down. You ready, Sam?
Yep.
Here we go. It goes down the line and it hits the end. So what's going to happen now?
Oh no, so there's some voltage and some current coming down, so there's power coming down. But then there's an open circuit, so the power can't be dissipated. Okay, so if I were to take a guess, the current has to be canceled out by something else.
Yeah, what is going to cancel out the current? We got a plus I going that way.
Oh, then let's call it a minus I being generated here and coming back.
So I minus comes back. And can you give me the sense of the current? Is it the same clockwise as it?
It would be, well, using your notation like that, this would be going counterclockwise.
And that's because it's returning back. So this actually is the return. So everything is upside down. So if I call the current I plus has an amplitude I0, then I minus
has to cancel out the I0, so
has
negative
to cancel
I0.
out the I0 because no current can flow. So minus I0. Well, wait a minute. Where does that come from? Why are we getting this? How does this happen? Because there's no other sources.
So it just happens to be generated at this boundary. So it's a reflected wave.
It's a reflected current wave. So are you telling me that the reflected current wave is generated with an amplitude the negative of the incident wave? And
Yeah,
then
that
both
sounds
of
about
these
right.
are traveling back and forth. It turns out that you can see that the voltage, we got to put the voltage here. There's obviously also a reflected voltage that's going to come back, but the sense of the voltage is the same. So the reflected voltage is with respect to ground, the top of the transmission line with respect to ground, but the sense of the currents are opposite. And that actually is the key analysis piece in all of transmission line analysis. And here we have an intuition way of doing it.
Yeah, that looks pretty good to me.
And there's no equations here, not a single one.